Good morning, everyone. Thank you for joining us today. We are pleased to present our benchmarking study entitled Benchmarking Large Language Model for Multi-Language Software Vulnerability Detection. This work is authored by Ting Zhang and Chengyang Yang, who shares equal contribution along with David Law. The research represents a collaborative effort between the School of Computing and Information Systems at Singapore Management University and the School of Computer Science at University of Sydney. This paper is currently available as a preprint on ARXIV under the identifier 250301449V1, dated March 3, 2025. Since it's a recent preprint, formal citation counts are not yet available, but as soon as it enters journal review, we expect citation metrics to follow. We choose to benchmark on this cutting edge work to provide timely insights into vulnerable detection. Software vulnerabilities remain a critically security concern, and automated detection tools have struggled to keep pace with the growing complexity and multilingual nature of modern code bases. While large language models have demonstrated impressive capabilities in code generation and understanding, no systematic evaluation exists for their use in software vulnerability detection across multiple programming languages. Our study poses three research questions. First, how effective are state of the art LLMs at detecting vulnerabilities in Python, Java, and JavaScript? Second, how do these LLMs compare against smaller code focused models and traditional static analysis tools? And third, can we improve LLM performance through data level or model level adaptation strategies? Thank you.
Thank you, Ishita. When it comes to dataset construction, for this research, the authors needed a reliable dataset of software vulnerabilities. So they used a national vulnerability database, which is a trusted source of real-world security issues in software. The data includes all reported vulnerabilities up to March 28, 2024. They focus on three widely used programming languages, Python, Java, and JavaScript. Uh, the dataset creation process involves several important uh, steps. First, they started by extracting CVEs. Next, they label the code like this. The versions of the function before the fix is marked as vulnerable code. The fixed version and any unrelated code are marked as non-vulnerable codes. To make sure the dataset didn't have a repeated code, they used MD5 hashing. Finally, they split the dataset in time-aware way. Uh, all data from before June 1st, 2023 was used for training, and data after that date was used for testing. Uh, in this study, the researchers evaluate different types of models and techniques to detect software vulnerabilities. First, they look at LLMs. These are powerful models with around 7 billion parameters trained on huge amount of code and text. They use models like CodeQueen 1.5, DeepSeek Coder, CodeGemma, and StarCoder 2, and CodeLlama. Then they compare these with smaller models, known as small language models. They are more lightweight and easy to train. The SLMs used in the study were CodeBird, Graph CodeBird, Unix Coder, CodeT5, and CodeT5 Plus. They also included two traditional static analytic tools like SemGrep and SonarQube. To adapt the models for the task, they use two main strategies, prompt engineering and fine tuning. Uh, this slide shows how well the models work for different programming languages. For Python and Java, the performance was low. The best F1 score was only around zero point 0.2. Here, prompt engineering methods like ICL and REG gave better results, but fine-tuning mostly failed. Uh, JavaScript gave much better results, which instruction tuning models reached an F1 score up to 0.44, and the best performance came from using QLoRa and fine-tuning. QLoRa fine-tuning. So the main takeaway is uh, different strategies work better for different languages. Uh, Also, data imbalance play a big role. JavaScript had more balanced data, which helps the model learn better. Thank you.
As we dive deeper into enhancing code security with LLMs, we evaluated coverage across common weakness enumeration categories. For Python, in-context learning covers 75 out of 80 CWEs. For Java, 33 of 37. However, JavaScript fine-tuned models only detect 13 of 43 types, indicating that fine-tuning can erase the broad vulnerability knowledge encoded in pre-trained LLMs. This finding underscores the need for careful calibration when adopting large models. Our second question compares LLMs to smaller code models and static analysis tools. In Python, even zero-shot LLMs outperform all SLMs. In Java and JavaScript, however, SLMs like GraphCodeBert and Code T5 Plus surpass LLM performance. Across all three languages, SimGrep and SonarQube perform worst, often by a large margin. The takeaway: no single approach dominates. The best tool depends on both language and model family. To explore data level strategies, we downsample non-vulnerable examples to create a more balanced training set. In Python and Java, this rebalancing improves F1 by over 0.02 on average. JavaScript shows mixed results because its original non-vulnerable to vulnerable ratio was already close to 2 to 1. Thus, data balancing helps when imbalance is severe but can offer little benefit if the ratio is moderate. Thank you.
Let's see the model level improvement. For model level strategies, the study tested ensembling via majority voting among LLMs alone, LLMs plus SLMs, and LLMs augmented with SAST outputs. Surprisingly, none of these ensembles outperformed the single best model. We attribute this to our time-aware data split. Models that look good on validation data don't always generalize. So naive ensembling may introduce noise rather than clarity. So let's move to the discussion and implications. From these findings, these practical lessons emerge. First, data imbalance dictates strategy. Few short prompt methods excel when positives are rare, while fine-tuning shines when classes are more balanced. Second, the volume of vulnerability examples matters. JavaScript with a large dataset achieved the highest absolute effort. Third, each LLM reacts differently to prompt versus tuning. So practitioners must pilot multiple adaptation methods rather than assume one fit will fit all. So let's move on to the threat to validity. So this study acknowledges several threats to validity. Construct validity may suffer because a fund does not fully capture trade-offs between precision and recall in real world. So internally, the study mapping of uh, outputs static tool outputs to function level labels in approximation. Externally, the study dataset is limited to NVD reported SGVs. So other vulnerability sources or language might shift the result. So at last, let's move on to the conclusion and future work of this study. So to conclude, this study finds no silver bullet for automated vulnerability detection. LLM adaptation must be both language and data aware. In future work, study plan to explore advanced prompt techniques such as chain of thought, reasoning, and dynamic retrieval alongside more sophisticated ensembling methods like stacking of meta-learners. Expanding to additional vulnerability repositories and programming languages will also help generalize findings. So thank you. This is our end of the presentation. Thank you.